Good afternoon, students. Myself, Dr. Sandeep Garg, Professor Electronics and Communication, Oriental College of Technology, Bhopal. Today, I am going to explain the subthreshold operation in MOS devices in the subject VLSI design as per the curriculum of RGPU. First of all, we will understand the concept of threshold voltage. Here, threshold voltage is the voltage that should be applied across the gate terminal so that the device will get turns on. Here, we can see this is the N-type MOS device. When we apply a positive voltage across the gate terminal, then it will attract the electrons in the p-type substrate towards the channel. As we increase that voltage, here this accumulation of electrons in the channel increases and the current through device will also increase. Now the voltage, the gate voltage at which the device completely turns on is called the threshold voltage of the device. The expression for the threshold voltage is given here. Vt is equals to Vt0, where Vt0 is the threshold voltage at 0 degree Kelvin, and gamma is the body factor, phi f is the Fermi potential, and VSB is the substrate to body voltage. Now the MOS device operates in different regions: cutoff region, resistive region, and saturation region. The device will operate in cutoff region when the gate voltage is less than the threshold voltage, and in that case ideally the drain current is 0. Second is the resistive region, in which the gate voltage is greater than the threshold voltage and drain to source voltage is less than VGS minus VT. In this, the device will operate in resistive or linear region, and the drain current is given by Kn by 2 W by L VGS minus VT into VDS minus VDS square by 2. So in this case, the device will operate in the linear region. Third case is the saturation region, when the drain voltage is greater than the VGS minus VT. Now, here one of the effects is the velocity saturation effect. In that case, as we increase the voltage across the device, the velocity of the electrons traveling from the source to drain region goes on increasing, and after a particular voltage it becomes constant. This effect is called the velocity saturation effect. Subthreshold conduction: when the device turns on below the threshold voltage, then that type of voltage is called the subthreshold, then that conduction is called subthreshold conduction. In that case, the device turns on even when the gate voltage is less than the threshold voltage. This may occur due to shorter channel lengths. This is the curve for subthreshold conduction. On the y-axis we have shown the drain current, and on the x-axis we have shown the drain to source voltage. Here we can see initially the current increases linearly with the increase in the drain voltage, and after that it becomes constant. Now the MOSFET operates in different regions. First one is the strong inversion region, means in that case the channel gets strongly inverted when the gate voltage is greater than threshold voltage, means when the device operates either in the linear or saturation region. Linear region when the device voltage VDS is less than VDS saturation, and saturation region when the device VDS voltage is greater than or equal to the VDS saturation. And second one is the weak inversion region, when VGS is less than VT. Now during the conduction and during the MOS formation, there are some parasitic resistances that occurs between the polysilicon and the drain region that will affect the operation of the device, and that will also increase the delay of. Now latch up in the CMOS device occurs due to the parasitics present within the substrate region and the well region. Here we can see that both when R well and R substrate are there as parasitic elements, and there are two parasitic transistors. When these two parasitic transistors turns on, then in that case there is a direct connection between the supply and the ground, and the current heavily flows that will cause the burning of the transistor and the CMOS device. So this is called the latch up. So because there is a latch between the two transistors.